Okay, so today we will be going over the coding set 4. This is going to cover C and C++ concepts. So let's get started. So number 1, you are given a linked list in ascending order. The function fun removes some special elements from the list. The list will be traversed by once. Which statements are justifying below for A, B, and C? So we have, looks like we have a basic linked list using a node structure. If current is null, then we return. Otherwise, if some condition hits, then it looks like we want to keep track of the next node and then free the next. So it looks like we want to skip over the next node. So looking through all 4 of these answers, we can deduce that C will accurately essentially like remove all the duplicate nodes in the linked list. So because they tell us that the linked list is in ascending order, running the code on C will every single time we hit a duplicate node, we will essentially just skip over that node and just free it up. And that's what's happening on line B. So current.data equals current.next.data. So we're essentially just shifting it over. So that brings it between C and D. Now for the condition, it has to be not equal to null, because if it were to do equals null, it will never hit inside this condition because the null check is already happening in the base case. So that leaves options between C and D. And now the difference between these two is last one on line C. So C is saying current dot next is next, while D is saying current equals current dot next. So because of this, we can say that it's C, because if we look at the last one here, this is just iterating current, but it's not actually doing anything. We already have the iteration occurring in the else statement here. So what needs to occur inside the if statement is by setting the next as a next, which is doing what we want to do, which is eliminate any duplicate values. So for number 1, we have C as our answer. Number 2, 2 strings are given, X and Y. Your task is to find the longest common subsequence. Suppose you have done this. If the length of the longest common subsequence is A and the number of subsequences you have obtained is B, then what is the value of 8 times B minus A? So a few things we have to know, that is, what is a common subsequence? So a common subsequence, in case you're not familiar, is a subsequence that is common to both strings. Now, what does that mean? That means a subsequence can be any number of a sequence of strings. It doesn't have to be adjacent, but it does have to keep the ordering. So for example, M and MP is a subsequence. Now, MP, they're not directly next to each other, but it is a subsequence because it retains the same order. So the longest common subsequence is the longest sequence of strings from both X and Y that are the same, but not necessarily like substrings, but just sequences within the string. So to answer this, we just have to look at these 2 strings and determine what way could we. So the first step would be to start at the string that's smaller. So in this case is X, and then trying to figure out if we can find a subsequence of this string already within Y. And we can actually do that. So we have M, N, M, P, P. we can find a subsequence from y because we have m and mpp. So already we can find that the longest subsequence is 5. So if you have the length, so we have a is equal to 5. And now we have to find b. So b is just the number of subsequences or of common subsequences. So after going through this, you'll eventually find that these are the subsequences. So we have m and mpp, and pp, n and pp, m and mp, and mmpp. So from here, there are 5 common subsequences between x and y. So because this b also equals to 5. So what is the value? Well, we have 8 times 5 minus 5. So that's 40 minus 5 is equal to 35. So we have C as our answer. Number 3, for 8 items and 6 slots in the hash table, calculate the following: the expected number of empty slots, the expected number of collisions, and expected number of items needed to fill all n slots. So in order to understand this problem, first, let's quickly go over what hashing is and how a hash table works. So a hash table, if you haven't heard of one already, or if it's new to you, it's a very common data structure we use to store data. It is a data structure that implements an associative array or dictionary that maps keys to values. So the big important thing to know about hash tables is that it maps keys to values, and then the way it maps those is by using what's called a hash function, which is a mathematical function that takes in the key, and then the value is what the output of that function is when you input the key. And usually that is the index of an array. So a hash table, it uses a hash function, like I said, to compute an index. It's also called a hash code. A hash code is the result of inserting the key into the hash function. So during the lookup of that table, or we could call it a dictionary, the key is hashed, and then the resulting hash indicates where the corresponding value is stored. So we can think of it as a kind of like an array or a dictionary. So if we have a value, right, like a value here, we input this value into the hash function, and then that spits out, let's say, like an index of where we would place this value. So if this spits out, let's say 1, then we'd place the 9 here. And now if you want to retrieve the index of this, we can use the same function. And the beautiful thing about hash tables is that the lookup and retrieval is always of 1, because it's just one compute of the hash. Now a collision is when 2 different keys end up being mapped to the same value. That's called a collision. So we have empty slots is when there's nothing mapped to this index. A collision is when you have more than 1. And then number 3 is expected number of items needed to fill all n slots. So this is going to be a really mostly just like a math question to deduce the equations needed to figure out what is the expected number of all these things. At the very base, in hashing items into a hash table, let's make this bigger. Of size k, the expected number of items that to any one location is n over k. So we have n is the number of items, and then k is the attached table. So to insert in any one of these values in the table is just a simple n over k, because it should have an equal chance of hitting any one of these locations. So this is the very base value of how we can derive any kind of equation, such as the number of collisions or empty slots. Now, the actual math that goes into deriving these is a whole nother explanation, but here I will write down the equations needed to get these values. So for the first one, the empty slots, the equation is this. So it's k times 1 minus, and then 1 over k to the power of n. Now, the expected number of collisions is the following. So we label that as C, is n minus k times 1 minus k minus 1 divided by k to the power of n. So this is the equation for calculating the expected number of collisions. And then lastly, the expected number of items needed to fill all n slots is the following. So we can just call it F for fill equals K, and then 1 plus LNK. So these are all estimates or accurate close approximations of the values of all of these. So now that we have the equations for these, all we need to do is just insert K and N into these respectively. So in this case, we have K is equal to 6, K is equal to 6, and N is equal to 8. So if you plug all these into these equations, you will eventually get A as the answer. So after that, it's just a matter of simple math where you plug it into these equations. There are m dice with n faces, number from 1 to n placed on a table. Harry shows a number y. Your task is to find the number of ways to get the summation value y of each face when all the dice are thrown. For example, you are given 2 dice with 4 faces. Harry shows you the value of y is 1. Obviously, the answer for number of ways is 0, because it is not possible to get 1 as the summation value from any faces of 2 dice. So it looks like we have it's another example of a almost but incomplete code, and they're asking us what is the 1 or 2 lines to fill in. So let's just start at the top and go through the code. So most of it is already done for us. We have, they make a matrices called table, and they set the size to D. Now D is M, and remember, M is over here, M dice. So D is the number of dice. And then the first one, F, that is corresponding to N, which is the faces. So F is the number of faces, and D is the number of dice, and then S is the desired sum. So the solution here is to create a table of for each dice value and then each face value. And then we're going to set everything to 0 except for the topmost corner. So if we can kind of draw this out here. So we have like a little table going on. So we have all these as 0. We set the top leftmost one at 1. And it looks like now we start traversing D. So D is the number of dice. So we have D is going down as the row. And then we have J, or I guess in this case it would be S. So S is going to be representing the different sums. And the basic logic of what we're trying to do is we're going to progressively fill in the table, and then incrementally counting how many dice it takes to get to this sum over here. And eventually we want to return this value right here, which is going to tell us how many ways that we can get S. And remember, S is going to be from 1 all the way to the desired S that we want. So let's say we have desired of like 12. This would be index 12. And therefore, that's why we want the corner. So we have 2 for loops, one going through the number of dice. So let's say we have like 5 dice here. We have 1, 2, 3, 4, 5. And then we have the second for loop going through the different amounts of sums. And here we have tab ij equals tab I of j minus 1. Now remember, j minus 1 would be the value right above ij because we're counting down. So if ij is here, j minus 1 is up here. And then j minus 1 would be the left corner. So the logic here is that we're going to build the possible number of ways for that sum, and then keep on building and extending all the way down this way. So this should, so eventually, if you look at the code and how it works, the final answer for this is D. So the if statement would be if j plus f minus 1 is greater than 0. Now this is, looks like it's between this one, and so these two have the same value, these two are not. In this case, you want to do if it's greater than 0. If it's less than 0, it'll never hit the if statements. That wouldn't make any sense. So A and B are out of the question. Now for the second part, we have table at I and j equals the current value minus table I minus 1 and then j minus f minus 1. And if you just plug that in and just run through the code, eventually you're going to get the value at the very corner that actually equals the number of different ways that you can roll the dice and reach the like desired sum that's sent here. So it's a lot of looping right here, but eventually this is the code that'll reach that desired output. Marks, so number 5, marks for different question asked for different forthcoming examinations have been decided by academic committee. For any examination, there will be 2 mark questions, 4 mark questions, 5 or 10. If the total marks obtained for a particular student is provided as an input, what will be the number of ways to get those marks? Okay, and then on the background of this code, what is the worst case runtime? So real quick, so runtime notation is always tracking the worst case scenario. And usually you want to look at how the loops are structured. So remember, for runtime, we only deal with n, which is the size of the input. And then the runtime, like the big O notation, it tracks what is the worst case of this algorithm over an infinitely large input. And how does it change as the input gets bigger? So one thing to keep in mind is the big O notation is not really tracking how efficient it is, though it is like correlating to that. It's more so tracking how the input grows or shrinks, how like the complexity grows or shrinks over an infinitely large input. So just going over the algorithm here real quick, looks like they make an array, fill it up with 0. They fill the first one with 1. And so since he's trying to find the total marks obtained, we go through every single from 2, 4, 5, and 10. We just go through and like add it up in those amounts of increments. And then eventually at the very last part, we can see how many possible ways it was to get to that number. So it's similar, really similar to last question. The question here is asking, what is the worst time runtime? So looks like we have a for loop here, but remember, since there's no curly brace for loop is only restricted to this right here. So this is just one loop. And then same thing for this one right here. And then same thing for this one right here. And now because 5 and 10, because 5 times 2 is 10, it's like a subsection of that. The runtime for the last for loop is still going to be O of n. So because you have 3 loops, one after each other, not inside each other, but after, and each of these loops is big O of n, we have big O of n plus O of n plus O of n. And that will still equal O of n because nothing changed about the complexity. So we have B as the answer here. All right, number 6, you are given a series of numbers, 2, 5, 10, 17, 26. The following code computes the difference between the nth term and then the n minus kth term, where there are n number of elements in the series. So k is a number that's within 1 to n minus 1. And we want to find what the missing code is. So this question is going to take a little bit of math. It's not as much programming heavy, but more so math and algorithmic heavy. And like we will go through that here. So let's look at the sequence first. So we can write out the sequence as the following. S equals, so we have 0 plus 2 plus 5 plus 10 17 plus 26 ... So we have S equals that. So another way to write this as the last part is we can do A of n minus 1. Now this is a subset n minus 1 plus a n ... So, and now we have another way to write it. So like we can take out the 0 and shift everything over. So S equals 2 plus 5 plus 10 plus 17 plus 26 plus a n minus 2 plus a n minus 1. Remember, this is the same thing. We're just shifted over by 1 and all that. So in order to solve this, we would actually, since this is going to be the shifted over one, we want to subtract this by this. So if we do that, we end up with S minus S is 0 equals, so now we have 5 minus 2, 10 minus 5, 17 minus 10. So we have 2 plus 3 plus 5 plus 7 plus 9. So it looks like we figured out what the pattern of the sequence is, and that is kind of like an exponential increase, where the increase increases by, so the increases by 2 each time. So 3, 5, 7, 9, with the exception at the very beginning, which has a 2 here. All right, so another way we can simplify this, and this is very math heavy, but this is the eventual output of what the simplification looks like. So this, so actually we have plus a of n here. Remember, this is a subset of n, so I'm just going to denote that with the parentheses. Okay, so now we have 2. So this will equal to 2 plus n minus 1 divided by 2, 3, minus n minus a of n. So this is the same, this is just a derivation of this previous step here. So now we have that. So now we have a of n. So now we can add a of n on both sides. So a of n equals, now we can simplify this side, this right here, into the following: 2 plus n minus 1 and plus 1 So a of n equals n squared plus 1. So now we can say a of n minus k equals n minus k squared plus 1. Because like we just substitute n minus k for n to get this. So that equals, so a n minus k equals n squared minus 2kn plus k squared. So now to find the difference, because remember, we want to find the difference between the nth term and the n minus k term. So difference will now equal to, so difference equals to n squared plus 1 minus n squared plus 2kn minus k squared. And that equals to 1 plus k 2n minus k. So this is looking pretty familiar. Looks like we have the final answer here. So yep, so we can look at here, look at final answer. This will match up with this. So we have D as the final answer. Now, again, this is not so much of a coding exercise, but more so of a math exercise to find the sequence here and to, deduce what this n minus nth term minus n minus k, or the nth term minus the kth term. All right, let's keep on going. Number 7. In Wonderland, ASCII values of 26 alphabets are given as A is 26, B is 25, etc., all the way to Z is 1. You are given a string S. Your task is to find whether the string is super ASCII or not. And looks like they define a super ASCII if the count of each character in the string is equal to its ASCII value. So it looks like for a string, if it has A, there needs to be 26 instances of that A, or if there is a Z, there can only be one Z. Okay, so let's just go through this. So we have a string, we dedicate 400 size for this char array. We create an array of 26 for the alphabet. We set it all to 0. Okay, so while looks like we're going through the entire str. So if it's greater than A, so if it is an actual character between A to Z, we want to do something. And then at the very end, we want to loop through it again and do something else. So the question is, what is that thing that we do? Okay, well, let's just look at the answers. Let's just look at what's different about each one and try to pick out things that cannot be true. So if we have this, we can say if this, then numbers stri plus plus. Now remember, we're dealing with characters which have an ASCII value. So because of that, if we're going to be counting things in here, we have to use this notation here. We have to use the z minus stri plus plus. So that it cannot be A or B. We want to look at between C and D. So for C1, it's either going to be Z minus STRI or STRI minus Z. Now the answer in this case would actually be C because the alphabet is counting backwards from A is 26. We want to place Z minus that because we have Z minus STRI. That'll equal the actual number count that we want to keep track of. And now for C2, that looks like pretty similar, but we can still go over that as well. If the numbers, so for C2, this is going to be the actual check outside this while loop, and that's going to be doing the actual check of, is this does this entire string pass the super ASCII test? And it looks like we have if numbers I is greater than 0, which it does check for both of these. And that does make sense because we want to make sure that we only want to check for super ASCIIs for ASCIIs that exist in the first place. We have numbers I. So in this case, again, this is another reinforcing of why C is the correct answer, because we want to see that if the numbers do not match up, if the value of the ASCII does not match up with the number of occurrences of that ASCII in the string, then we want to say that it fails. So this has to be if it's not equal to. So another reason why the answer here has to be C. So with that in mind, we can see that if that's the case, if they're not equal, then we set ASCII to 0, which is exactly what we want to see right here. Okay, so you're given a 4 times 4 matrix. Your task is to perform some operations. So we have a few operations. We have a rotate anti-clockwise by 90 degrees. We have a update the element at row P and column Q by X. And then we have compute the sum of boundary elements. So yeah, it looks like the first question here is looking at the first part, which is rotate 90 anti-clockwise. So this is just a kind of a basic algorithm to just rotate every single character in a 4 times 4 array. So if we go a little further here, so I picked apart the answer because it was pretty large, but this is going to be the final answer, B. And the reason is because there's going to be 4 operations. So as you can see in the double for loop here, we're going to be looking at the 4 quadrants of the 4 times 4. And for each quadrant, we're going to perform these operations. So we have the top left corner. And if you're going to rotate anti-clockwise, so if you look at it kind of like this. So this right here, if you're going to rotate it anti-clockwise, that's going to end up right here. This right here, you're going to rotate anti-clockwise, is going to end up here. So you can think of this as like the left corner, and then this is going to be where it's getting placed. So where is this left corner? So what's happening to this left corner? Well, it's equal to I of j and n minus I minus 1. So if you look at all 4 of these code and trace through it, you can pretty quickly see that this is accounting for every single one of the 4 corners that we're going to end up rotating. So first we sent a temp at I. So for example, if we look at this just from the 4 corners on the outside, we can kind of visualize what's happening here. So we sent the temp as this, and then we replace this with this value. So now this value gets replaced here. And then now we're looking at this value. This value gets replaced by this one. Now we're looking at this value. This value gets replaced by the bottom corner here. And then lastly, this value, since we have a temp variable stored, we set the temp as whatever was here. We set this down to there. So as you can see in the code, these 4 lines accounts for the 4 kind of rotations that happen within each subquadrant of this square. So we have here, the final answer is B. Now, if you look at C2 as well, we want to see over here, we have another double for loop. One second. So C2 is looking at the boundary elements, and this like we know is correct because the boundary elements can be found by I is 0, j is 0, or I is n minus 1, or j is n minus 1. So these are the 4 boundaries where I or j is at the beginning, or if it's at the end, which is n minus 1. So with all this in mind, we have there are 4 possibilities. The right one is this one right here, answer B. All right, so we have two integers, x and n. Your task is to find the number of ways to express x as a sum of nth powers of unique natural numbers. It is given that n is between 1 and 20 inclusive. So they give us a quick example here where x is 100 and n is 2. So we can represent these in multiple ways. We could either do 100 or 10 squared. We can do 8 squared plus 6 squared, and then we can keep breaking it up. So like right off the bat, we can tell that the answer here is going to be something recursive because we're going to keep breaking it up further and further. Okay, so let's look at F1. So we have the main here, which calls count ways, and then count ways we'll call the recursive function here. So as you can see here, I've highlighted the final answer B, and the reason is we can go through really quickly right now. So the general logic of how to solve this is we need to keep track of the value. Now, each time we break it down recursively further, we have to subtract the current x from the value, because if, like, let's say we're at 100 and we're trying out, let's say 6 squared. The next time we break it down, we want to do 100 minus that 6, or 100 minus that 36, and we're going to keep breaking it down that way. So val equals x minus and then num to the power of n. So now with that, you can then return both cases where we do the value and then also the new. So keep in mind, so like this value was just that x, but we took away like one of those cases. And then eventually the base case, as you can see here, is once we hit the value 0, which is saying once we hit, like once we subtract enough from the total sum, so that there's no more to be found powers of, then return 1. So that's the base case there. And of course, if it's less than 0, we want to return 0. So the two cases are if f1, so f1 if you put in the value, and then f1 if you put in x. So with that in mind, if you trace through it, you'll quickly see that B is the final answer that actually gets us the number of total unique ways to get to the sum. All right, so as you can see, these are all the 10 questions. This one was a little harder than previous weeks, so definitely take the time to run through the code like this, just to see how everything works. And then lastly, we have our 2 websites that I can bring up right here. So we have like the Indian version of the site over here, crackingitjobs.com. And then from right here, you can create an account and join the coding club right here. So this is a quick little demo of the website. Yeah, so this is the kind of where you log in. So you would log in here, or if you don't have one, you make an account. And as you can see, we post all the videos of our explanations here. And then the other site that we've recently created for our US students is this one right here, poccomu.com/coding-club. It's fairly similar, but this is for the US students. And if you're a US student and you're interested, this is where you would sign up. All right, well, thank you very much, and I will see you guys next time.